Hello, everyone, and welcome to Signals, Systems, and Signal Processing with Wolfram U. The topic of this lesson is inverse Z-transform. We previously defined the Z-transform of a sequence X of n. The inverse Z-transform is formally defined by the contour integral shown here. As it was the case with the Laplace transform, for the case of discrete-time LSI systems, linear shift-invariant systems, we don't need to take the contour integral. For a rational Z-transform X of Z given in the general form shown here, we can use the method of partial fraction decomposition to express the rational Z-transform in terms of superposition of simple terms whose inverse transforms are known. Each term of the expansion corresponds to one of the roots of the denominator polynomial, and so we will go over this method for two different cases, where the roots of the denominator are distinct or when we have repeated roots for the denominator. In the case where we have n distinct poles, pk's, the Z-transform X of Z may be expanded into a linear combination of first-order terms as shown here. The constants ai's are called the residues and are obtained using the formula shown here. Now, assuming that the region of convergence is where the absolute value of z over pi is greater than 1, each term of the partial fraction expansion has an inverse transform of the form shown here. Adding these terms gives the expression for the sequence X of n. As an example, given the proper rational function shown here for the Z-transform of a sequence and the region of convergence as indicated here, let's use the method of partial fraction expansion to find the sequence X of n. First, let's find the inverse Z-transform using the Wolfram language. Now, to find the inverse Z-transform by hand, let's first write the Z-transform in terms of positive powers of Z. This way, it will be easier since the steps will be similar to partial fraction decomposition of rational Laplace transform. Note that the expression in terms of positive powers of Z is improper, and so we'll first have to reduce the order of the numerator polynomial by dividing it by Z, as shown here. Applying the method of partial fraction decomposition, we get the two simple terms shown here. To find the values of A1 and A2, we take the limits as defined in the formula for the residues for A1 and A2. Using these values, we can write the decomposition of X of Z and find the inverse Z transform of each term one by one and add them together to get the sequence X of n. When the denominator polynomial of a proper rational Z transform has a root with multiplicity k, the expansion of the Z transform X of Z takes the form shown here, and the constants ai's are found using the formula indicated here. Then, assuming that the region of convergence is absolute value of z over p greater than 1, each term of the partial fraction expansion has an inverse transform of the form shown here. Let's look at another example. For the Z transform given here, with repeated roots for the denominator, let's find the inverse Z transform. The inverse Z transform can be found using the Wolfram language as shown here. We can also list the first few samples of the sequence. Now, to find the inverse Z transform by hand, we start by writing the Z transform in terms of positive powers of Z and divide the expression again by Z. Using the general formula for coefficients ai of the kth order pole, we find the values for A3, A2, and A1. Using these coefficients, we can put together the decomposition of the Z transform X of Z, and each term in the decomposition has a known inverse Z transform. For the first term, we have the expression shown here, which we can also verify using the Wolfram language, and the inverse Z transform of the second term, verified by the Wolfram language, and the third term. Putting together these three terms, the sequence X of n in the time domain will be given as shown here. We can again also look at the first few samples of the sequence. Let's look at another example. Given the Z transform GZ as shown here, We want to find and plot the poles and zeros of the Z-transform and also plot the magnitude of the Z-transform. Finally, we want to obtain the causal sequence G of n in time domain. We can use the Wolfram language to find and plot the poles and the zeros, and we can show the magnitude of the Z-transform in decibels evaluated on the complex plane. Next, we take the inverse bilateral Z-transform of the Z-transform to find the sequence in the time domain. We can also plot the sequence to show how it changes over time. The examples that we have looked at so far all assumed system causality, and therefore an ROC that spans the exterior of a circle marked by the largest pole. Although this is probably the most common case encountered in practice, it's also important for us to consider other cases for the ROC for a given Z-transform. For example, for the Z-transform shown here, with the two poles 1/2 and 4/5, we will have three different cases for ROCs. Let's find the inverse Z-transform for each of these three different cases. For the first case, we can use the Wolfram language and find the inverse bilateral Z-transform for the specific ROC as shown here. We can also plot the sequence to see how it changes over time. We have a causal or right-handed sequence. If we were to find the inverse Z-transform by hand, we look at the partial fraction expansion of x of z as shown here and find the values of the constants a and b. Putting together these values, we have the expansion of the Z-transform. And we find the inverse Z-transform of each of the terms in the decomposition. Putting together these two terms, we get the same causal sequence for x of n. For the second case, again, we find the inverse bilateral Z-transform using the specific ROC to find the sequence in time domain. We also plot it and notice that we have an anti-causal or left-sided sequence in time domain. For the third case, we again find the inverse Z-transform, and when we plot it, you can see that we have a two-sided sequence. In this lesson, we focused on taking the inverse Z-transform by the method of partial fraction expansion. We went over several examples where we evaluated residues for both distinct and repeated roots. And we also showed several examples of finding the inverse Z-transform for different ROCs.